All right, here's a little bit of video work to help supplement the lab that we were working on in class. Now, we had an apparatus that looked like a PVC contraption made out of a T out of PVC. So it looked a lot like this. And I had you all put masses on the outside edge. I believe, as I recall, the masses I gave you were equal to 100 grams. And that though you could set your own lengths here, we would have some R, some radius for those, of about something like 26-ish centimeters. 26 centimeters. Now, that can fluctuate a little bit. If you have them in a little bit further, you might be 25, even 24. It all depends on the data that you've collected, how you set it up. I think the very edge of these is about 27 centimeters, so you might have a little bit more than 26, depending on where you put those. All right. Then we wrapped a string around this part, and we pulled it out at a constant force from anywhere from 1 Newton to 5 Newtons. So you all set the force, and you recorded the time it took for 1 rotation. Furthermore, you started from rest. There are a few things that we need to do. So the data that you have is force and time. Okay, but what I actually want you to generate a graph of is to test Newton's second law for rotation, which says the sum of torques is equal to the moment of inertia times the angular acceleration, which means while we recorded the force and the time, we actually want to put those in, do a little bit of math to those to actually get them in terms so that we can graph the torque and the angular acceleration. So let's start with the easy one. Let's start with force. I can turn force into a torque. Torque is equal to our force, the magnitude of our force, times the magnitude of the lever arm, times sine of the angle between them. That's a simplification of the cross product. Now, if you imagine from above, we have the PVC pipe like this, and we have a string wrapped around it, and then it wrapped around over to here, and you all would pull straight off here. And this would begin to spin, but at every given point, you would have, here's the lever arm that you are applying that at, basically the radius of the PVC pipe, and it points directly to the right in my drawing, and your force points directly down. So the first thing that'll point out is, no matter how you rotate this, the way you all had it set up, theta of the angle between them, theta, is actually going to be equal to 90 degrees, or pi over 2 if you prefer to think in terms of radians. But in either case, sine of 90 or sine of pi over 2 is going to give you a positive 1. We can actually forget that part. So the force, which we recorded, great. We're going to use our forces, 1 Newton, 2 Newton, 3 Newton, 4 Newton, and so forth, to actually come up with the torque. The other thing that we need is D, the lever arm that force is applied at, and coincidentally, the radius, I should say, of that PVC pipe, which, let me see, I believe I gave you in class, but I measured it with calipers. We find that D is equal to 0.0105 meters, or something very close to that. It's about, it's a little over 2 centimeters in diameter, the pipe. And so that's what I have marked as being the lever arm for the PVC. Hopefully that matches what I gave you in class. If not, we'll try and get that updated. Regardless, that's what we've got. So we've got D, great. I also provided you with R and M, although R might fluctuate based on where you all set that. In either case, we found a way that we can go through and we can get our torques. We're going to take our forces and we're going to multiply them by the lever arm, the radius of this PVC pipe. Now we need to deal with the time. The time is what's going to help us find the other thing that we want, which is the angular acceleration. As I change the torque for the same moment of inertia, for the same masses being distributed the way they are, my acceleration should change, and on top of that, we should have a linear relationship. All right, time and angular acceleration. A great place to go for that are going to be our kinematic equations. And our kinematic equation would be, well, let me give you the original one that you're more used to seeing. Delta x equals v naught times time plus 1/2 at squared. Now, when we change this over to our rotational analogs, delta x becomes theta, our angular displacement. V naught is omega naught times time plus 1/2 alpha t squared. Come on board. Anytime. T squared. Great. Here's where we bring in some information. We've got t, so we can fill that in, and we want alpha. So we're going to need our angular displacement, theta. Well, theta, you recorded the time for one complete rotation, so theta is 2 pi radians. That's one complete rotation. On top of that, I told you to start from rest. That means omega naught is actually 0 radians per second. So we get the following. 2 pi equals 0, which I'm just going to leave off, 1/2 alpha t squared. If I want to find alpha, then I'm going to multiply by 2 and divide by t squared, and I get the following. Alpha will be equal to 4 pi, 2 times 2 pi, divided by t squared. As a side note, if I asked you on an exam what you would do to linearize the data, and you had force and time, or I should say things like torque and time, you would go through and you would graph one of them. One of the axes would not be the force versus time. Or I'm sorry, the graph would not be force versus time. I know that for many of you, you just take what you've been given, this is what you changed, this is what you recorded, and you robotically put it into a graph. What we're trying to do is get you set up where you can make a graph that lets you draw conclusions and gives you measurements about things in the real world. So we're not going to take force by itself, we're going to take force times the lever arm, and the other axis is actually going to be 4 pi divided by t squared. So I'm going to be doing versus t squared, basically. Anyway, so this is setting up the equations that I'm about to show you how to put into Excel.